Welcome back. Continuing our discussion of vicinal halohydrin formation. We've got a very important question to answer here. Why doesn't bromide attack like it did before? And the answer has to do with the fact that water is both a reactant and, more importantly, solvent. So this molecule here that we created, this triangular intermediate, is surrounded by not bromide ion. When you made this, you made one bromide ion, but it is surrounded by water. Water will be the attacker. You're saying water is not as good as an attacker. It doesn't have a minus charge. You've got a pretty good argument there. But it's got lone pairs like bromine does, and there's a lot more of it. So it's the creature of opportunity that will attack the more substituted carbon there. But how do we get the triangular intermediate here? You might think that the alkene attacks the bromine in Br2. You would be wrong. Sitting on the shelf in the back room is a pre-mixed solution of bromine and water that will be added to the alkene when this reaction is desired. So the bromine and water have already reacted. So the first step in this mechanism is to acknowledge that the bromine and water have already reacted in the bottle, and water hits the bromine. It's a backside attack. No triangle made here. And what you get is this intermediate here and a bromide. But more importantly, there's a bromine with water attached. And that's an oxonium because the oxygen now has 3 bonds. That is what the alkene will react with. It has lone pairs on bromine, 3 if you're keeping score. And the mechanism is identical to before. Sorry, I'm a little in tight there, but that lone pair is coming back to which carbon? All day? The more substituted carbon. And water is leaving. So water is also produced here, but don't forget, you don't have to wait for water to be produced. This molecule is surrounded by water. Water will be doing the backside attack on the more substituted carbon. It's triangle day. We're attacking the backside on the more substituted carbon all day. And we're going to get an intermediate here. And what's it gonna look like? It's gonna look a lot like the product. But the oxygen still has 2 hydrogens. And what do we have here? It's an oxonium. One of the reasons we studied acid-base chemistry so early in this course is because it comes up in a lot of other things in the remaining parts of organic chemistry. This is the conjugate acid of the final product. It is a strong acid. It will not take much of a base to take that H. Some of you want to use the bromide. I say I'm okay with it, but I'm not that happy. 2 reasons why water is a better choice of base for the neutralization. Water will take the H, and I'll give you the reasons shortly. And that'll become hydronium. It's a side product. You really don't have to show side products on tests. Why is water the better choice? Good question. Let's make it a formal question. Why is water a better base? That's interesting. Spelling a base. And Br minus. And that's a good question. Let's answer that question shortly. Whoa, don't want to move that. Okay, two-part answer. PKB part. I need PKBs. Yeah, they never go away, people. H2O and Br minus. Stronger base will be a better choice. To do the PKB of water, you need to know the pKa of its conjugate acid, which is called, don't tell me it's hydroxide, that's the conjugate base of water. What's the conjugate acid of water? Hydronium. What's the pKa of hydronium? Because pKa plus pKb for a conjugate acid base pair equals 14. So pKb is 14 minus pKa of the conjugate acid, which is -3, hydronium, 17. pKb for bromide is 14 minus HBr's pKa, which is -5. Yes, it's been rounded to -5, but the story is this is slightly stronger base. Water is a stronger base by a factor of 100 than bromide. Remember, it's a log scale and the difference is 2. 10 to the power of 2 is 100. That's one part of the answer. The other part of the answer is this sentence. Water is both a reactant and solvent. I wonder if I can copy paste it. Nope, not going to be so lucky. How about shortening it? Water is everywhere. That's what solvents do for you. They're everywhere. So what's this thing going to encounter first? Water, which this thing's surrounded by, or a bromide ion, which you made like one of? I think you answered your own question. Water's a better choice of base. Keep this discussion in mind when we talk about oxymercuration, and the story changes a little. And can we do a quick review of regioselectivity and stereoselectivity in this reaction? Why is it called Markovnikov? The electronegativity of oxygen is 3.5. The electronegativity of bromine is 2.8, sorry. More electronegative atom on the more substituted carbon is called Markovnikov. And the reason was we did a backside attack on the more substituted carbon with this water. Stereoselectivity, the new groups, one is up and one is down. We call that anti. Why did that
Doctor?
happen? Yes.
Sorry to interrupt, but what happened to the last bromine that we were talking about?
It's just floating around, watching the proceedings. We call it a spectator now.
Oh, okay.
Just hanging around, not doing anything. Okay. So let's do a journal version of this. Journal entry right here. And we'll steal the title. And we'll do an acyclic one. We've been using the same ring all day. We should have the mechanism up there so we can use it down here. Maybe go one size smaller here. There we go. And here is an alkene. We wanted it black. And we'll go with a, I don't know, a little bigger here. Put an ethyl there. And we'll do, we did BR, we'll do ClCl. And we'll have water present for this one. And our result will look like this. The water is more the O on the water is more electronegative than the Cl. And it will end up on the more substituted carbon. And the I lost a carbon here. The Cl will end up on the less substituted carbon. And one will be sticking out of the page. And one will be behind the page. And there we have it. How does the reaction start? Oh, I keep getting rid of the original, don't I? First thing you had to do was react the water with the halogen. Let's do it. Water has to, you need to show me a lone pair. Without the lone pair, I'm going to tell you right now, you draw the arrow without the lone pair. Here's the result. I'm going to say you lost a quarter point. You don't have an arrow starting at any electrons. You have it starting at a labeled oxygen atom. Arrows must start at a pair of electrons, period. There's a pair of electrons. It's called a lone pair. Now you have to draw the result. And we have a chlorine attached to OH2 with a plus charge. I don't even need to see the chloride, so I'm not going to put it. Yes, you made a chloride right here. Chloride leaves, Cl minus. Don't need to see it. Don't draw it. Look at the reaction above. What was the next step? Pi electrons attack halogen. Water leaves. Lone pair comes back to which carbon? The theme of the day? More substituted carbon. Which of these two carbons down here is more substituted? It's the one on the left. So lone pair on my halogen. Alkene attacks the halogen. That's a good question. Why did it attack the halogen and not the oxygen? It's a good question. If you attack the oxygen and then the halogen leaves, then oxygen's still going to be a cation. This is not the nature of reacting oxonium ions. When it was acid-base chemistry, what did you do? Look, you didn't attack the oxygen to make it neutral. You attacked the hydrogen attached to it, and then it got its lone pair back. Same story here. Attack the halogen attached to it, so get its lone pair back. That's the nature of oxonium ions. Don't attack the oxygen, please. Doesn't happen. You're going to have to draw me a triangle, and this one's going to disappear. So let's look ahead. We're going to draw our triangle, and then water's going to attack the more substituted carbon, and the carbon that got attacked is going to break its bond to the halogen. Halogen gets a lone pair. So let's draw our triangle. We'll put it right here. That's a little far over, isn't it? You needed one more intermediate after this one. So, yeah, always looking for shortcuts. They don't always happen. And the triangle will have chlorine between these carbons. Don't forget, it's a plus chlorine. You're going to lose a half point if you leave the plus off. It's a chloronium. And water will be the attacker. And which carbon will be attacked? It's a good question. It's been the same answer all day, hasn't it? H2O is the attacker. And it attacks the more substituted carbon. And we get a new intermediate. And maybe I'll be lucky this time. No, I don't think so. Thought so. It looks a lot like that intermediate. That's why I wanted to do this. What's the only difference? Okay, the O is green. It's got one H, but it also has a second H. It's an oxonium. You didn't show bonds breaking from O to H, and please don't, because it doesn't happen until it's a strong acid. Got to make a strong acid before you neutralize it. Don't try to come up with new improved mechanisms because they're shorter. You might not be obeying the rules of reality, and you don't get points for that. Science class. OH2, water, comes and grabs the H. It's the better base, and there's more of it. And there you go. You get your vicinal halohydrin. Vicinal on adjacent carbons, halo, halogen, hydrin, alcohol on the more substituted carbon. And it's got the regioselectivity that's called Markovnikov with the more electronegative O on the more substituted carbon. And it's got the stereoselectivity called anti, one group sticking away from the page and one behind. And that's that. Save this. And then we're going to do our final triangle of the day. We'll do a preview and then pick it up. Oh, yeah, there we go. Pick it up after this. Oxymercuration is, as the name suggests, a reaction that adds oxygen to one side of an alkene and mercury to the other. And mercury is not a very desirable commodity, especially when attached to carbon. Most of those molecules are toxic. So getting rid of the mercury is going to be something we're going to learn as well. So let's go back to our slight variation. And the chemicals we're going to use here, mercury bonded to acetate twice. That's mercury II acetate. The II from your inorganic chemistry days just means its charge is +2. And here's our alkene. Make sure you don't think it's bonded to mercury already. So that's 2 of the ingredients. The oxygen, here we're going to start with water. H2O can be replaced by alcohols or carboxylic acids. You'll get different results. We won't explore those until later. And that will give us our oxymercuration result that we see here. And I know you didn't learn the electronegativity of mercury, but you did learn the electronegativity of oxygen, and you do know it's the second most electronegative element that we know. And there will not be any changes to that. The top two are The top two are oxygen and fluorine. So oxygen is more electronegative than mercury. We expect to see it on the more substituted carbon. Why? Because it's triangle day, and it will be in the form of OH, much like it was before. More substituted carbon, and the mercury will be on the less substituted carbon. Triangle involved also gives an anti-regioselectivity. I'm going to use a short form that we'll explain after the break. OAC, that's an acetate. It's an acetyl group with an O, that's an acetate. These are acetates here as well. And I will see you very shortly.